Tonight, we are going to talk about something that might fundamentally change how you think about humanity's place in the universe. Not distant theories that might be proven someday. Not science fiction dreams of terraforming Mars in the next century. Not speculation about what might exist in galaxies billions of light years away, but real worlds, orbiting real stars, where liquid water might be flowing right now, where atmospheres might be thick enough to protect whatever walks or swims beneath them, where, just maybe, life has already taken root and is thriving at this very moment while you watch this video. We have discovered 5 planets that are not merely interesting curiosities for scientists to catalogue and study. These are worlds that researchers across the globe believe could genuinely actually support life as we know it. Not in some distant future, after centuries of preparation and technological advancement. Not after human intervention with massive terraforming projects, but right now, today. This very moment as you sit wherever you are, these worlds might harbour living organisms going about their daily existence, completely unaware that we are looking for them. These planets orbit stars you have almost certainly never heard of. Stars with catalogue designations rather than proper names. Located in regions of space that we have barely begun to explore with our most powerful instruments. Some of these worlds are closer to us than you might think, practically next door in cosmic terms. Others are farther away, light years multiplied by dozens or hundreds, at distances that make detailed study extraordinarily difficult with current technology. But all of them, every single one, share one remarkable and essential property. They sit in that narrow, precious zone around their parent stars, where temperatures are just right. Not so hot that water boils away into vapor and escapes to space. Not so cold that water freezes into solid ice and remains locked away forever. The Goldilocks zone, as it is often called, the habitable zone, as scientists prefer to name it. That special distance where liquid water, that essential ingredient for all life we know, can exist on a planetary surface. Before we dive deeply into each of these fascinating worlds, if this kind of exploration captivates your imagination and makes you think about the cosmos in new ways, a quick like or subscribe helps more than you might realize. It tells the algorithm that thoughtful, detailed, in-depth content matters to viewers, that people genuinely care about understanding the universe beyond our small world. And it helps me continue creating these long-form journeys into the cosmos, these deep explorations of topics that deserve more than superficial treatment. Now, let us begin this journey together. To truly understand what makes these 5 planets so special and why scientists are so excited about them, we need to start with fundamental principles. We need to understand what we mean when we talk about habitability. What conditions must a planet possess to potentially host life? We know with absolute certainty of one habitable planet, Earth, our home world, the only place in the entire known universe where we have confirmed that life exists. And from Earth, from studying our own world in excruciating detail, we can extract principles that might apply elsewhere in the cosmos. Life as we know it, every organism that has ever existed on Earth, from the simplest bacteria to the most complex mammals, requires liquid water. This is not an arbitrary choice or a limitation of our imagination. Water is an extraordinary molecule with properties that make it uniquely suited for supporting the chemistry of life. Water is an excellent solvent, capable of dissolving a vast array of chemical compounds, which allows the complex chemical reactions necessary for life to occur. It remains liquid over a remarkably wide temperature range compared to other simple molecules, from 0 degrees Celsius to 100 degrees Celsius at standard atmospheric pressure, giving life a substantial window to operate within. When water freezes, it expands and becomes less dense, which means ice floats. This seemingly simple property has profound implications, as it prevents bodies of water from freezing solid from the bottom up, allowing liquid water to persist beneath ice sheets and aquatic life to survive through cold periods. Almost every biochemical reaction that we know about, every process by which living cells maintain themselves and reproduce, happens in aqueous solution, dissolved in water. So when astronomers search for habitable planets, they are fundamentally searching for places where liquid water could exist on the surface, or perhaps in subsurface environments. This single requirement narrows the search considerably. Get too close to a star and water boils away, lost to space, as the molecules gain enough kinetic energy to escape the planet's gravitational pull. Travel too far from a star and water freezes solid, locked in ice that might never melt, unavailable for the chemistry of life. In between these extremes lies the habitable zone, sometimes called the circumstellar habitable zone, to be more precise. But calculating the boundaries of the habitable zone is not a simple matter of measuring distance. It depends critically on the star's temperature and luminosity. A hot, bright star like Sirius has its habitable zone much farther out than our Sun's habitable zone. A cool, dim red dwarf has its habitable zone much closer in, sometimes closer than Mercury orbits our Sun. But the star's properties are only part of the equation. The planet's atmosphere plays an equally crucial role. A thick atmosphere with substantial greenhouse gases like carbon dioxide, methane, or water vapor can warm a planet that would otherwise be frozen, effectively extending the outer boundary of the habitable zone. Venus, despite being closer to the Sun than Earth, demonstrates how a runaway greenhouse effect can make a potentially habitable world into a hellish oven. Mars, farther from the Sun than Earth, might have been warmer and wetter in its distant past when it possessed a thicker atmosphere. But the loss of that atmosphere to space has left it cold and dry today. A thin atmosphere, or no atmosphere at all, means that even a planet sitting right in the middle of the traditional habitable zone might be frozen and lifeless. Habitability depends on many other factors that we are only beginning to understand fully. A magnetic field generated by a molten iron core, creating a dynamo effect, can protect a planet's atmosphere from being stripped away by the stellar wind, the constant stream of charged particles flowing outward from the star. Earth's magnetic field has protected our atmosphere for billions of years. Mars, lacking a significant magnetic field, gradually lost its atmosphere, and with it, any liquid water that once flowed on its surface. Plate tectonics, the slow movement of crustal plates driven by convection in the mantle, plays a vital role in regulating Earth's climate over geological timescales. The carbon silicate cycle, in which carbon dioxide is removed from the atmosphere through weathering of rocks and then returned through volcanic activity, helps maintain stable temperatures over millions of years. Without this geological recycling, atmospheric carbon dioxide could either build up to dangerous levels or be depleted entirely, pushing the planet out of the habitable range. The right balance of land and ocean matters too. Too much land, and you might not have enough water to maintain a stable climate. and provide moisture for weather systems. Too much ocean, and you might lack the geological processes associated with continents. Earth sits at roughly 70% ocean coverage, which seems to work well. The presence of a large moon, like Earth's moon, can stabilize a planet's axial tilt over long periods. Earth's tilt of about 23.5 degrees gives us seasons, but more importantly, it remains relatively stable over millions of years. Mars, with no large moon, has an axial tilt that varies wildly over time, leading to extreme climate swings that would make the development of complex life much more difficult. Habitability, we are discovering, is extraordinarily complicated. It is not just about being at the right distance from the right kind of star. It is about having the right combination of properties, the right size to maintain geological activity and retain an atmosphere, the right composition to provide water and other volatiles, the right atmospheric pressure and composition to maintain liquid water at the surface, the right magnetic field to protect that atmosphere, the right orbital characteristics to ensure stable conditions over long periods. But despite these complications, we are learning. As our instruments improve and our understanding deepens, we are finding candidates that meet more and more of these criteria. The 5 planets we will discuss in detail tonight are not perfect Earth analogues. Perfect Earth twins might not exist, might be extraordinarily rare. Some of these worlds orbit red dwarf stars that are cooler and smaller than our Sun, stars that present their own unique challenges for habitability. Some are larger than Earth, super-Earths with higher gravity that would feel quite alien to any human visitor. Some are lightly tidally locked, showing the same face to their star forever, creating a permanent day side and permanent night side with no sunrise or sunset. But all of them, in their own distinctive ways, might harbor the fundamental conditions necessary for life to exist. All of them sit in that precious habitable zone. All of them might have liquid water. And where there is liquid water, there might be life. Let us now turn our attention to these 5 extraordinary worlds, starting with the one that is closest to us. Planet 1, Proxima Centauri b. The nearest star to our Sun, the closest stellar neighbor we have in the entire galaxy, is a small red dwarf with a catalogue designation Proxima Centauri. It is part of a triple star system, the Alpha Centauri system, which includes 2 Sun-like stars, Alpha Centauri A and Alpha Centauri b, that orbit each other. Proxima Centauri orbits this pair at a great distance, perhaps 1 trillion miles away from them, far enough that it takes millions of years to complete one orbit around the binary pair. Proxima Centauri is tiny by stellar standards, with only about 1/8 the mass of our Sun and about 1/7 the diameter. If you placed it next to the Sun, it would look like a small, dull red coal next to a blazing yellow sphere. Its surface temperature is only about 3000 Kelvin, compared to the Sun's 5778 Kelvin. It produces only about 0.17% of the Sun's luminosity, meaning it is hundreds of times dimmer than our star. And yet, this unremarkable little star, this dim red coal in the cosmic furnace, holds one of the most tantalizing prizes in all of astronomy. Located just 4.24 light-years away, Proxima Centauri is home to a planet, and that planet orbits within the habitable zone. In the cosmic scheme of distances, 4.2 light-years is practically next door. If our galaxy were the size of the continental United States, Proxima Centauri would be about 6 feet away from us. A light year, the distance light travels in 1 year at its incredible speed of 186,000 miles per second, equals about 6 trillion miles. 4.2 light years means about 25 trillion miles. That is still an almost incomprehensible distance. But in galactic terms, it is neighboring. The discovery of this planet, announced in 2016, sent ripples of excitement through the astronomical community and captured the imagination of space enthusiasts worldwide. For the first time, we had confirmed a planet orbiting within the habitable zone of the very closest star to our own. If we were ever going to send a probe to another star system, if we were ever going to make the leap to studying an exoplanet up close, this would be the logical first target. They named it Proxima Centauri b, following the standard naming convention where the star gets the name and planets are designated with lowercase letters starting with B. Sometimes it is called simply Proxima b for brevity. And from the moment of its announcement, it became the closest known exoplanet in a habitable zone, a title it still holds today. Let me give you the fundamental facts about this world, the properties we have been able to measure from Earth using various observational techniques. Proxima b is slightly larger than Earth, though we do not know its exact size, because we have never observed it transiting across the face of its star from our vantage point. Its minimum mass is about 1.06 or 1.07 Earth masses, depending on which recent measurements you look at. This is a minimum mass because we do not know the exact orientation of its orbit. If we are looking at the orbit edge on, this is its true mass. If we are looking at it at an angle, it could be more massive. Recent estimates that account for the most likely orbital inclination suggest its true mass might be closer to 1.44 Earth masses, making it a super-Earth, slightly more massive than our world. It orbits its star every 11.19 days, zipping around Proxima Centauri in less than 2 weeks. The orbital distance is tiny, only about 0.0485 astronomical units. For reference, 1 astronomical unit is the average distance between Earth and the Sun, about 93 million miles. Proxima b orbits at less than 5% of that distance, about 4.5 million miles from its star. Mercury, the innermost planet in our solar system, orbits the Sun at 0.39 astronomical units, about 8 times farther than Proxima b's orbital distance. This sounds dangerously, impossibly close, and it would be completely unsurvivable if Proxima Centauri were a Sun-like star. At that distance from our Sun, any planet would be roasted, its surface turned to molten rock, any atmosphere boiled away instantly. But Proxima Centauri is not a Sun-like star. It is a red dwarf, cool and dim. To receive the same amount of stellar energy that Earth receives from the Sun, a planet must orbit much, much closer. At its orbital distance of 0.0485 astronomical units, Proxima b receives roughly the same amount of stellar radiation that Mars receives from our Sun, perhaps slightly less. Not the same as Earth, but not terribly different either. Climate models suggest that surface temperatures on Proxima b could range from about -12 degrees Celsius on the low end to slightly above freezing on the high end, depending critically on the planet's atmospheric conditions, its albedo or reflectivity, and how heat is distributed around the planet. If the planet has no atmosphere, or a very thin atmosphere, the surface would likely be too cold for liquid water, except perhaps in the warmest regions. But if it has a substantial atmosphere, with greenhouse gases like carbon dioxide or methane, surface temperatures could easily be warm enough for liquid water to exist in large quantities. This is where the situation becomes simultaneously fascinating and frustratingly complicated. Proxima b might have the right temperature for liquid water. The orbital distance places it squarely in the habitable zone. But does it actually have water? Does it have an atmosphere? Can that atmosphere persist against the hostile environment created by its red dwarf star? These are the critical questions, and we do not yet have definitive answers. Red dwarf stars, despite being the most common type of star in the galaxy, are tricky hosts for life. They have some properties that seem advantageous. They are incredibly long-lived, burning their hydrogen fuel at such a slow rate that they can remain on the main sequence, maintaining stable luminosity for trillions of years. Our sun will last about 10 billion years in total before exhausting its hydrogen fuel and beginning its transformation into a red giant. Proxima Centauri will last about 4 trillion years, 400 times longer. This gives life on any planets orbiting red dwarfs an almost unlimited amount of time to arise and evolve, to experiment with different forms, to potentially develop intelligence and technology. But red dwarfs also have properties that seem hostile to life, especially when the stars are young. Red dwarfs are magnetically active, especially in their youth. They produce powerful flares, sudden releases of magnetic energy that flood the surrounding space with radiation and charged particles. These are not gentle solar flares, like the ones we occasionally see from our sun. These are violent eruptions, sometimes thousands or even tens of thousands of times more powerful than the largest solar flares ever recorded. Proxima Centauri is no exception to this rule. It is a flare star, officially designated as such because of its regular flaring activity. Observations have recorded numerous flares over the years, some increasing the star's brightness by a factor of several times for periods of minutes or hours. These flares emit not just visible light, but intense ultraviolet radiation and X-rays, as well as streams of charged particles that make up the stellar wind. For a planet orbiting as close as Proxima b does, this flaring activity could be catastrophic for any atmosphere. The intense radiation can strip away atmospheric molecules, particularly lighter ones like hydrogen, literally blasting them into space. Over billions of years, this atmospheric erosion could completely strip away an Earth-like atmosphere, leaving behind a barren, airless rock like Mercury or our moon. But there is hope. Some recent research suggests that Proxima b might have been able to retain an atmosphere despite the harsh conditions. One possibility is that the planet started with an extremely thick atmosphere, perhaps orders of magnitude thicker than Earth's. Even after billions of years of erosion by stellar wind and flares, enough atmosphere might remain to support liquid water. Think of it like a bank account that started with an enormous balance. You can make withdrawals over a long period and still have substantial funds remaining. Another possibility involves volcanic outgassing. If Proxima b is geologically active, volcanoes constantly erupting and releasing gases into the atmosphere, the rate of atmospheric replacement might match or exceed the rate of atmospheric loss. This creates a kind of equilibrium where the atmosphere is constantly being both lost and replenished, maintaining a relatively stable state over geological time. Earth's atmosphere is maintained partially through this process. Volcanic activity releases carbon dioxide, nitrogen, sulfur compounds, and other gases that would otherwise be lost to space or locked in rocks. There is also the fascinating and critical question of tidal locking. At its orbital distance, Proxima b almost certainly experiences tidal forces from its star strong enough to have locked its rotation to its orbit long ago. This is the same phenomenon that has locked our moon's rotation to Earth, which is why we always see the same face of the moon. For Proxima b, tidal locking means one hemisphere, the day side, perpetually faces the star, while the opposite hemisphere, the night side, forever faces away into the darkness of space. For many years, scientists thought tidal locking essentially ruled out habitability. They reasoned that the day side would become scorchingly hot while the night side would freeze. And most problematically, any atmosphere would condense and freeze out on the night side, removing the atmospheric pressure needed to support liquid water anywhere on the planet. The planet would become uninhabitable, with all its water ice locked away on the dark hemisphere. But recent, more sophisticated climate models have painted a more optimistic picture. These models show that an atmosphere can transport heat from the day side to the night side through atmospheric circulation. Winds would develop, driven by the temperature difference between hemispheres, carrying heat around the planet. The day side might not be too hot because some of its heat is constantly being carried away. The night side might not be too cold because it is constantly receiving heat transported from the day side. And crucially, the atmospheric pressure remains relatively uniform across the planet, preventing the atmosphere from freezing out entirely on the night side. These models suggest that at the boundary between day and night, in a zone of permanent twilight called the terminator region, temperatures could be remarkably stable and moderate. Not too hot, not too cold, just right for liquid water. This twilight zone might be the most habitable region on the planet. Imagine, if you will, standing on the surface of Proxima b, assuming it has a solid, accessible surface, and an atmosphere you could breathe or at least survive in with protection. If you are on the day side, looking up, you see an enormous red sun hanging motionless in the sky. Proxima Centauri would appear about 3 times larger in angular diameter than the sun appears from Earth, covering a significant portion of the sky. But it would not be the blazing yellow-white orb we know. It would glow a dull, deep red, like a coal in a dying fire. The light would be dim, perhaps comparable to late twilight on Earth, just after sunset, but before full darkness falls. Everything would be bathed in this eerie red glow, and shadows would be soft and diffuse. That sun would never move. No sunrise, no sunset, no passage of time marked by the sun's position. It would hang there, fixed, eternal, perhaps varying slightly in brightness when flares erupted on its surface. The landscape around you might be rocky, perhaps volcanic, with signs of recent or ancient lava flows. The geology could be dominated by volcanic features if the planet has substantial tidal heating from the gravitational interaction with its star. If water exists on Proxima b, it might pool in low-lying areas, forming seas or lakes on the day side where temperatures are warmest, or it might be trapped as ice on the night side, or in polar regions, only melting in specific areas where geothermal heat rises to the surface. The distribution of water would depend critically on the atmosphere's ability to transport heat and moisture around the planet. The sky itself would be fascinating. If the atmosphere is substantial and has clouds, you might see cloud formations quite different from Earth's. The patterns would be dominated by the day-night circulation, with clouds possibly forming in a ring around the terminator, where rising air from the day side meets descending air from the night side. If the atmosphere is thin or clear, the sky might be filled with stars, visible even on the day side because the star is so dim. And in that sky, you might see Alpha Centauri A and Alpha Centauri B, the two sun-like stars that form the rest of the Alpha Centauri system. From Proxima B's distance, they would appear as brilliant stars, far brighter than any star visible from Earth except the Sun, but still point sources rather than disks. If you could travel to the night side, the experience would be entirely different. No sunlight at all, ever. The landscape would be illuminated only by starlight, by auroras if the planet has a magnetic field and experiences aurora-like phenomena from stellar wind interactions, and by any artificial light if there were inhabitants with technology. The temperature would be much colder than the day side, though not as extreme as once thought if the atmosphere is doing its job of heat transport. The terminator region, that twilight zone between day and night, might be the most interesting and potentially habitable area. Permanent twilight, with the sun sitting right at the horizon, half its disk visible. Temperatures would be moderate, neither too hot nor too cold. This might be where life would concentrate if it exists, occupying a relatively narrow band that circles the planet like a belt. And if life does exist on Proxima b, it would be adapted to conditions utterly alien to anything on Earth. Photosynthetic organisms, if they evolved, would need to harness the dim red light of the star, requiring pigments and chemical processes quite different from the chlorophyll and photosynthetic pathways we see on Earth. Plants, if something analogous to plants exists, might be black or very dark in color, absorbing every available photon rather than reflecting green light like Earth's vegetation. Life might cluster in the twilight zone, as mentioned, avoiding the extremes of permanent day and night, or perhaps it would spread across the day side, living beneath protective layers of water that filter harmful ultraviolet radiation, similar to how life on Earth first evolved in the oceans. Or maybe life would flourish on the night side, drawing energy not from sunlight, but from geothermal sources, from volcanic vents and hot springs, much like the extremophile bacteria that live near hydrothermal vents in Earth's deep oceans. Ecosystems that thrive in complete darkness, powered entirely by chemistry. The possibilities are tantalizing, and the questions are numerous. Scientists have been working hard to learn more about Proxima b ever since its discovery. In 2025, a new instrument called the Near Infrared Planet Searcher, or NIOPS, installed at La Silla Observatory in Chile, delivered its first science results. This spectrograph is specifically designed to hunt for planets around small, cool stars like red dwarfs. One of its first major accomplishments was confirming the existence of Proxima b with greater precision than previous measurements, validating its properties and refining our understanding of its orbit. NIOPS also helped confirm the existence of another planet in the system, Proxima d, a smaller world orbiting even closer to the star, definitely too hot for life as we know it. And crucially, NIRPs helped rule out a previously claimed third planet, Proxima c, which some studies had suggested might exist farther out in the system. The refined census shows Proxima Centauri has at least 2 confirmed planets, with Proxima b being the potentially habitable one. But the biggest question remains unanswered. Does Proxima b have an atmosphere? Scientists are working on ways to find out. One approach involves searching for signs of atmospheric absorption in the star's light, looking for spectral signatures that would indicate gases surrounding the planet. This is extraordinarily difficult because Proxima b does not transit its star from our vantage point, which means we cannot use transmission spectroscopy, the technique that works so well for transiting planets. Another approach involves direct imaging. Despite the planet's proximity, directly imaging it separate from the glare of its star is incredibly challenging. The star is billions of times brighter than the reflected light from the planet, but future extremely large telescopes, with their enormous light-gathering power and advanced adaptive optics and coronagraphs to block starlight, might be able to detect Proxima b directly and study its reflected light spectrum to search for atmospheric signatures. There are also proposals for interstellar missions, serious scientific proposals, not just science fiction, to send probes to Alpha Centauri. The Breakthrough Starshot project, funded by private philanthropists, aims to develop technology for tiny light-sail spacecraft that could be accelerated to 20% the speed of light using powerful lasers. At that speed, a probe could reach Proxima Centauri in about 20 years. It would not slow down or orbit, just zip past at tremendous velocity, taking photographs and measurements during a brief encounter lasting only hours or minutes. But even that flyby would provide invaluable data, potentially answering the question of whether Proxima b has an atmosphere and whether it has water. Proxima b represents both enormous promise and profound frustration. It is the closest potentially habitable planet we know. It sits right next door in cosmic terms, tantalizingly within reach. And yet, with current technology, it is almost as inaccessible as planets thousands of light years away. We can detect it, we can measure its basic properties, but we cannot yet determine if it truly is habitable or if it is just a barren, airless rock baked by stellar flares. The next decade will bring new data, new telescopes, new instruments, new techniques. Perhaps we will find evidence of an atmosphere. Perhaps we will discover biosignatures, chemicals that indicate life. Or perhaps we will determine that Proxima b is uninhabitable, hostile to life despite being in the right place. Either way, the search will continue. Because Proxima b, the planet next door, will always be the first place we look when we search for our neighbors in the cosmos. Planet 2, LHS 1140, about 48 light years away from Earth, in the constellation Cetus, the whale, orbits a planet that has emerged in recent years as one of the single most promising candidates for habitability in the entire galaxy. A planet that recent observations from the most powerful space telescope ever built suggest might not just have water, but might be dominated by water to an extent that dwarfs even Earth's oceans. A planet that could be one of the best places in the universe to search for alien life. It is called LHS 1140b. The designation refers to its host star, LHS 1140, which is a catalogue number from the Luyten half-second catalogue, a survey of stars with high proper motion. The B designation indicates this is the first planet discovered around this star, following the standard naming convention. When astronomers first discovered this planet in 2017 using the M-Earth South Array, a series of robotic telescopes in Chile, specifically designed to search for transiting planets around small nearby stars, they were intrigued but uncertain about its nature. The planet appeared to be large and relatively low in density, which could mean two very different things. It could be a mini Neptune, a small gas giant with a thick hydrogen and helium atmosphere, making it inherently inhospitable to life. Or it could be a super-Earth, a rocky planet larger than Earth, potentially with substantial water, making it a prime candidate for habitability. For years, the question remained open. Different studies suggested different compositions. Some models favored the mini Neptune interpretation. Others leaned toward the super-Earth scenario. But the available data was not sufficient to definitively distinguish between these possibilities. Then came the James Webb Space Telescope observations in late 2023, and everything changed. Let me take a moment to explain why this observation was so significant and what it revealed. The James Webb Space Telescope, or JWST, is the most powerful infrared observatory ever placed in space. Launched in December 2021 and positioned at the second Lagrange point about 1 million miles from Earth, JWST is specifically designed to study faint infrared light from distant cosmic sources. Among its many capabilities, it can perform transmission spectroscopy of transiting exoplanets with unprecedented precision. Transmission spectroscopy works like this. When a planet passes in front of its star from our point of view, a tiny fraction of the star's light filters through the planet's atmosphere before reaching us. Different molecules in the atmosphere absorb different wavelengths of light, leaving distinctive signatures in the spectrum. By carefully analyzing the starlight during a transit and comparing it to the starlight, when the planet is not transiting, astronomers can identify which molecules are present in the atmosphere. The James Webb observations of LHS 1140b, conducted using the NIRISS instrument, the Near Infrared Imager, and slitless spectrograph, one of JWST's 4 main instruments, produced results that excited the exoplanet community immensely. The data showed that LHS 1140b definitively does not have a thick, hydrogen-rich atmosphere. This ruled out the mini Neptune scenario conclusively. The planet is not a gas giant. It is something else. The observations also provided tantalizing, though not yet definitive, evidence for a nitrogen-rich atmosphere. Nitrogen is the dominant gas in Earth's atmosphere, making up about 78% of the air we breathe. Finding nitrogen on an exoplanet would be extraordinarily significant because nitrogen atmospheres are associated with rocky, potentially habitable worlds rather than gas giants. But even more exciting than the atmospheric hints was what the refined mass and radius measurements implied about the planet's composition. LHS 1140b has a radius of about 1.73 Earth radii and a mass of about 5.6 Earth masses. When you calculate the density from these numbers, you get a value significantly lower than what you would expect for a pure rocky planet like Earth or Venus. Earth's density is about 5.5 grams per cubic centimeter. LHS 1140b's density is only about 3.8 grams per cubic centimeter. This lower than expected density strongly suggests that a significant fraction of the planet's mass is composed of something less dense than rock, and that something is almost certainly water, lots and lots of water. Analysis of the planet's bulk properties indicates that up to 10 to 20% of its total mass might be water. For comparison, Earth's oceans, despite covering 70% of our planet's surface, constitute only about 0.02% of Earth's total mass. If LHS 1140b has 10 to 20% water by mass, it is not just an ocean world. It is a water world beyond anything we have in our own solar system, possibly even more water-rich than the icy moons Europa or Enceladus when measured as a fraction of total mass. Try to picture what this might mean for the planet's structure and appearance. Models of LHS 1140b's interior suggest something like this. At the center, there is probably a rocky core, composed of silicates and iron, similar to Earth's interior, but proportionally smaller. Surrounding this core is an enormous layer of water, hundreds of kilometers deep, possibly thousands of kilometers deep. This is not liquid water throughout, at least not in the sense of water we are familiar with from Earth's oceans. Deep down, near the core, pressures are so immense that water exists in exotic, high-pressure forms. Perhaps as hot, high-pressure ice phases that remain solid despite being much hotter than boiling water at Earth's surface. This sounds paradoxical. Ice that is hot, but under extreme pressure. Water's phase diagram allows for solid ice phases at temperatures of hundreds of degrees. Moving outward from the core through the water layer, pressure decreases and temperature decreases. Eventually, you reach regions where water exists as a liquid. This could be a vast global ocean, completely encircling the planet, without any land masses or continents at all. The depth of this ocean could dwarf Earth's deepest ocean trenches. The Mariana Trench on Earth reaches down about 11 kilometers. The ocean on LHS 1140b might be 100 or even 1,000 times deeper in places. Above this global ocean would be the atmosphere, assuming the planet has retained one. The hints of nitrogen detected by James Webb suggest this atmosphere might be substantial, possibly similar in composition to Earth's, dominated by nitrogen with smaller amounts of other gases. Now, here is where the planet's likely tidal locking becomes critically important for understanding its structure and potential habitability. LHS 1140b orbits its star every 24.74 days at a distance of about 0.0921 astronomical units. At this distance from a red dwarf star, tidal forces would have locked the planet's rotation billions of years ago. One hemisphere, the day side, perpetually faces the star. The opposite hemisphere, the night side, perpetually faces away. This creates a unique temperature distribution across the planet. The day side, especially the point directly facing the star, called the substellar point, receives constant radiation. Even though the star is a red dwarf and dim, the constant heating over billions of years would maintain relatively high temperatures on this hemisphere. The night side, receiving no direct starlight ever, would be much colder. If LHS 1140b is a water world with a global ocean, what happens to that ocean given this temperature difference? Models suggest something remarkable. On the day side, centered on the substellar point, there would be a region of liquid water ocean, possibly quite warm, heated by the constant starlight. Estimates suggest this ocean might be roughly comparable in size to Earth's Atlantic Ocean, perhaps smaller, a vast body of liquid water. Moving away from the substellar point toward the terminator, temperatures drop. The liquid ocean transitions into ice, probably a thick ice sheet kilometers deep. This ice continues across the terminator and covers most or all of the night side. On the coldest parts of the night side, the ice might be extremely thick, perhaps tens or even hundreds of kilometers thick. But beneath that thick ice shell, especially on the night side, there might be another ocean. The planet's interior still contains heat from its formation, heat from radioactive decay of elements in the core, and possibly heat from tidal flexing if the planet's orbit has any eccentricity. This geothermal heat flows upward through the rocky core and into the water layer. On the night side, where the surface is frozen solid, this heat might maintain a layer of liquid water beneath the ice. A subsurface ocean similar to what we believe exists on Jupiter's moon, Europa, or Saturn's moon Enceladus. But on a much larger scale, think about the implications. As LHS 1140b might have two oceans, or perhaps one continuous ocean with ice in the middle. A surface ocean on the day side, exposed to starlight, where photosynthesis could occur if life exists. And a subsurface ocean on the night side, dark and isolated from the star, where life could exist in eternal darkness. Powered by chemical energy from hydrothermal vents on the ocean floor, similar to the chemosynthetic ecosystems found near Earth's deep ocean vents. The atmosphere, if it exists as the data suggest, would play a crucial role in heat distribution. Winds would develop, driven by the temperature difference between day and night. Air would rise on the warm day side, creating low pressure. It would flow toward the night side at high altitude, descend as it cools, creating high pressure, and then flow back toward the day side at lower altitude, creating a global circulation pattern. This would transport heat from day to night, moderating temperatures across the planet and possibly preventing the entire night side from freezing solid. The surface gravity on LHS 1140b would be significantly higher than Earth's due to the planet's greater mass. With 5.6 Earth masses compressed into only 1.73 Earth radii, surface gravity would be about 3 times Earth's gravity. If you weigh 150 pounds on Earth, you would weigh 450 pounds on LHS 1140b. This high gravity would have profound effects on any life that might evolve there. Organisms would need stronger structural support to deal with the crushing weight. Flight would be much more difficult, possibly impossible for anything but the smallest creatures. But swimming in the ocean would be less affected since buoyancy helps counteract gravity. Imagine what it might be like to explore LHS 1140b if humans ever developed the technology to visit. Approaching from space, you would see a world unlike anything in our solar system. The day side might appear blue, like Earth, from the liquid water ocean. But surrounding this blue region would be white, a vast expanse of ice covering everything from the mid-latitudes outward. The night side would be completely white, a frozen hemisphere, possibly with cracks and fractures in the ice, revealing darker material beneath. Landing on the dayside ocean would be challenging due to the high gravity. A spacecraft would weigh 3 times its Earth weight, making descent and ascent much more fuel-intensive. But once on the surface of the ocean, you could sail or swim in this alien sea. The water might be relatively warm, perhaps comparable to tropical oceans on Earth, depending on your distance from the substellar point. The star would hang motionless in the sky, a dull red sun about twice the diameter of our sun, as seen from Earth, bathing everything in red light. The water might be clear, or it might be filled with life, with microorganisms or perhaps even larger creatures. If photosynthesis has evolved, there might be analogues to plankton, microscopic organisms floating in the sunlit surface waters, forming the base of an aquatic food chain. larger organisms might feed on these photosynthetic microbes, and still larger creatures might prey on them, creating an ecosystem possibly as complex as Earth's oceans. Diving beneath the surface, you would descend into an ocean far deeper than any on Earth. The sunlight would fade quickly, absorbed and scattered by the water. Soon you would be in darkness, broken only by bioluminescence, if life exists and has evolved light-producing organs. The pressure would increase relentlessly as you descend. At the depths, comparable to Earth's deepest ocean trenches, about 11 kilometers, the pressure reaches over 1,000 atmospheres. On LHS 1140b, descending hundreds of kilometers, the pressure would be tens of thousands of atmospheres or more, enough to crush any conventional submarine. Eventually, if you could somehow survive and continue descending, you might reach the ocean floor, the boundary between the water layer and the rocky core. Here, in the cold darkness, volcanic vents might erupt, spewing superheated water and minerals. Life might cluster around these vents, drawing energy from chemical reactions rather than sunlight, an entire deep ocean ecosystem thriving in eternal night. Traveling to the night side would present different challenges. The surface here is frozen, but beneath the ice, that subsurface ocean might be accessible. You would need to drill or melt through kilometers of ice to reach it, but once through, you would enter an ocean that has never seen starlight. This ocean might be cold, just above freezing, kept liquid only by the heat from the planet's interior. It would be completely dark except for any bioluminescence from organisms adapted to this extreme environment. Life in such an environment would be truly alien. No photosynthesis possible in the eternal darkness. All energy would come from chemical sources, from geothermal heat and chemical reactions. Organisms might cluster around hydrothermal vents, as on Earth, or they might drift in the water column, feeding on organic particles that rain down from where? Without photosynthesis producing organic matter at the surface, the base of the food chain would have to be chemosynthetic bacteria, organisms that build organic molecules from inorganic precursors using chemical energy. The prospects for life on LHS 1140b are genuinely exciting. The planet appears to have liquid water in abundance. It might have a substantial atmosphere. It orbits within the habitable zone of a star that, while active, is stable enough to allow life to develop. The planet has been in this state for billions of years, giving life ample time to arise and evolve. But significant challenges remain. The high gravity would affect how life develops and what forms it could take. The tidal locking means life must adapt to either eternal day or eternal night. With no day-night cycle like Earth has, the red dwarf star produces flares that could be harmful to life on the day side, though life beneath the ocean surface would be largely protected. And we still have not definitively confirmed the nitrogen atmosphere, though the evidence is promising. Scientists emphasize that more observations are needed to confirm the atmospheric composition and to search for biosignatures, gases that would indicate life. Future observations with James Webb are planned, using more observation time and more sophisticated techniques to improve the data quality. One approach involves observing multiple transits and averaging the results to reduce noise. Another involves observing at different wavelengths to search for specific molecular signatures. The ultimate goal is to detect biosignature gases. On Earth, oxygen is the primary biosignature, a gas that would not persist in the atmosphere without constant replenishment by photosynthetic life. Other potential biosignatures include methane, which can be produced by both geological and biological processes; phosphine, a gas that on Earth is only produced by life or industrial processes; and various other compounds that are hard to produce abiotically. If we detect clear biosignatures on LHS 1140b, it would be one of the most profound discoveries in human history. Proof that life exists beyond Earth. Proof that we are not alone. Proof that the universe, rather than being a dead expanse, is alive. Even without biosignatures, LHS 1140b stands as one of the most fascinating worlds we have discovered. A possible ocean world with a breathable atmosphere, located close enough that we can study it in detail with existing and near-future technology. If humanity ever sends an interstellar probe to study an exoplanet up close, LHS 1140b would be near the top of the target list. For now, we can only observe from afar, piecing together clues from the faint light that reaches us across 48 light-years. But each observation brings us closer to understanding this remarkable world and answering the question that has captivated humanity for millennia. Are we alone in the universe? Planet 3, TRAPPIST-1. In February 2017, astronomers held a press conference that generated headlines around the world and sparked intense excitement throughout the scientific community and among space enthusiasts everywhere. They announced the discovery of not one, not two, but 7 Earth-sized planets, orbiting a single star, all of them packed into orbits so compact that the entire system, star and all 7 planets, would fit comfortably inside the orbit of Mercury. 3 of them located squarely in the habitable zone, the region where liquid water could exist on their surfaces, and all of them close enough to Earth that detailed study with current and near-future telescopes might actually be possible. The star is called TRAPPIST-1, an unassuming red dwarf located about 40.7 light-years away from Earth in the constellation Aquarius. The name TRAPPIST stands for Transiting Planets and Planetsimals, small telescope, the Belgian-operated telescope in Chile that first detected transits of these planets in 2015 and 2016, when subsequent observations with NASA's Spitzer Space Telescope and ground-based observatories confirmed the existence of not just 2 or 3, but 7 planets. The discovery became one of the most significant in exoplanet science. The 7 planets are designated TRAPPIST 1b, C, D, E, F, G, and H, labeled in order from closest to farthest from the star, following the standard naming convention. Each of these worlds is roughly Earth-sized, with radii ranging from about 0.77 to 1.13 Earth radii. This makes them all terrestrial or rocky planets rather than gas giants. Their masses range from about 0.3 to 1.3 Earth masses, with similar variation. But among these 7 fascinating worlds, one stands out as perhaps the most promising candidate for habitability. One planet that sits in what scientists call the sweet spot of the system, neither too close to the star where temperatures might be too high, nor too far where temperatures might be too cold. One world that has been the focus of intense observational campaigns with the James Webb Space Telescope and other instruments. That world is TRAPPIST-1e, the 4th planet from the star. Let me describe the fundamental properties of this remarkable planet and why it has captured so much scientific attention. TRAPPIST-1e has a radius of 0.92 Earth radii, making it just slightly smaller than our home world. This is extraordinarily close to Earth's size. By comparison, Venus has a radius of 0.95 Earth radii, so TRAPPIST-1e falls right between Venus and Earth in terms of size. The planet's mass is about 0.692 Earth masses, or roughly 70% of Earth's mass. This makes it less massive than Earth, despite being nearly the same size, which implies a slightly lower density. The planet's density is about 5.4 grams per cubic centimeter, compared to Earth's 5.5. This is remarkably similar and strongly suggests that TRAPPIST-1e is indeed a rocky planet with a similar internal structure to Earth. It probably has an iron core, a silicate mantle, and a thin, rocky crust. The slightly lower density might indicate either a smaller iron core relative to its total size, or possibly the presence of some water or lighter materials in its composition. TRAPPIST-1e orbits its star at a distance of just 0.02928 astronomical units, or about 4.4 million kilometers, roughly 2.7 million miles. That is incredibly close. To put it in perspective, that is less than 3% of the distance between Earth and the Sun. The innermost planet in our solar system, Mercury, orbits at 0.39 astronomical units, more than 13 times farther from the Sun than TRAPPIST-1e orbits from its star. But remember, TRAPPIST-1 is not like the Sun. It is an ultra-cool red dwarf, one of the smallest and coolest types of stars that can still fuse hydrogen. With only about 8% of the Sun's mass and about 11% of the Sun's radius, TRAPPIST-1 is barely massive enough to be classified as a star rather than a brown dwarf. Its surface temperature is only about 2500 Kelvin compared to the Sun's 5778 Kelvin. It produces only about 0.05% of the Sun's luminosity, making it roughly 2,000 times dimmer than our star. Because TRAPPIST-1 is so cool and dim, a planet must orbit very close to receive enough energy to maintain liquid water. At its orbital distance of 0.029 astronomical units, TRAPPIST-1e receives about 60.4% of the stellar energy that Earth receives from the Sun. This is about a third less than Earth's solar constant, but significantly more than Mars receives, which is only about 43% of Earth's solar constant. This places TRAPPIST-1e squarely in the middle of the habitable zone for its star. It is not at the inner edge, where a planet risks becoming too hot, like TRAPPIST-1d might be, and it is not at the outer edge, where a planet risks becoming too cold and frozen, like TRAPPIST-1f might be. It sits right in the Goldilocks zone, where conditions are just right. The planet's equilibrium temperature, which is the temperature it would have if it absorbed all incoming starlight and radiated it away as thermal infrared radiation with no atmosphere, ranges from about 225 Kelvin to 246 Kelvin, depending on the assumptions you make about the planet's albedo, its reflectivity. In more familiar units, that is about minus 48 degrees Celsius to minus 27 degrees Celsius, or minus 55 to minus 17 degrees Fahrenheit. Now, these equilibrium temperatures sound quite cold, well below the freezing point of water. But this is where atmospheres become critically important. These equilibrium temperatures assume no atmosphere, or an atmosphere with no greenhouse effect. Earth's equilibrium temperature without greenhouse warming would be about minus 18 degrees Celsius, well below freezing. But Earth's actual average surface temperature is about 15 degrees Celsius, a difference of 33 degrees. because our atmosphere contains greenhouse gases like carbon dioxide, methane, and water vapor that trap heat. If TRAPPIST-1e has an Earth-like atmosphere with similar greenhouse warming, its surface temperature could easily be above the freezing point of water over much of its surface. Models suggest that with a few tenths of a bar of carbon dioxide, roughly comparable to the carbon dioxide content of Earth's atmosphere, though somewhat higher, TRAPPIST-1e could maintain surface temperatures warm enough for liquid water. The orbital period of TRAPPIST-1e is just 6.09962 days. A year on this planet lasts only about 6 Earth days. This might seem strange, like time is compressed. But from the perspective of someone living on the planet, if that were somehow possible, the day-night cycle would not exist in the way we experience it. The planet is almost certainly tidally locked to its star, just like the moon is tidally locked to Earth. Tidal locking occurs because of gravitational interactions between the planet and star. When a planet orbits very close to its star, the star's gravitational pull creates tidal bulges on the planet, slight distortions from a perfect sphere. If the planet is rotating relative to these bulges, there is friction that gradually slows the planet's rotation. Over millions or billions of years, this friction causes the rotation to synchronize with the orbital period. The planet ends up showing the same face to its star at all times. For TRAPPIST-1e, this means one hemisphere, the day side, perpetually faces the star, while the opposite hemisphere, the night side, forever faces away. From the day side, the star never sets. From the night side, the star never rises. There is no dawn, no dusk, no cycle of day and night as we know it. This creates unique conditions. The day side is constantly heated by starlight. Even though the star is dim, the constant heating over billions of years maintains relatively high temperatures. The night side receives no direct starlight and would naturally be much colder. Without an atmosphere to transport heat, the day side would be scorching and the night side would be frozen. But if TRAPPIST-1e has a substantial atmosphere, everything changes. Atmospheric circulation, driven by the temperature difference between day and night, would transport heat around the planet. Winds would blow from the hot day side to the cold night side, carrying heat energy with them. This would cool the day side and warm the night side, moderating temperatures across the entire planet. Climate models of tidally locked planets in the habitable zone suggest that atmospheric heat transport can be quite effective. The day side does not become as hot as you might fear. The night side does not freeze solid as you might expect. Instead, temperatures are surprisingly moderate, with the coldest regions on the night side still warm enough that liquid water could persist in equatorial regions, and the hottest regions on the day side not so hot that water boils away. The terminator, the boundary between day and night, would be a zone of permanent twilight. Here, the star sits right at the horizon, part of its disk visible above, the horizon part below. This region might have the most stable and moderate climate, neither too hot nor too cold, and could be particularly favorable for life if it exists. Now let me address what we actually know about TRAPPIST-1e's atmosphere, because this is where the science becomes both exciting and frustratingly ambiguous. Since the announcement of the TRAPPIST-1 system, one of the top priorities for astronomers has been to determine whether these planets have atmospheres. Planets around red dwarf stars often lose their atmospheres to stellar wind and radiation, especially during the star's youth. when it is most magnetically active and produces frequent powerful flares. The innermost planets, TRAPPIST-1, B, and C, orbit so close to the star that they almost certainly have lost any primordial atmospheres they once had. Observations with James Webb in 2023 essentially confirmed that TRAPPIST-1b has no significant atmosphere. Or if it does, it must be extraordinarily thin. TRAPPIST-1c's situation is still somewhat ambiguous, with different studies reaching different conclusions, but most evidence suggests it also lacks a substantial atmosphere. TRAPPIST-1d, the third planet, sits right at or just inside the inner edge of the habitable zone. James Webb observations in 2025 suggested that if it has an atmosphere, it must have a large molecular weight and be largely devoid of infrared active gases like carbon dioxide and water vapor. This is a strange result that scientists are still trying to understand. It might indicate a very unusual atmospheric composition, perhaps dominated by nitrogen with few other gases. Or it might indicate that the planet actually has little or no atmosphere, but TRAPPIST-1e, farther from the star and presumably less subject to atmospheric erosion, might have retained an atmosphere. This is the key question that multiple James Webb observing programs have tried to answer. In late 2024 and into 2025, several teams observed transits of TRAPPIST-1e using James Webb's near-infrared spectrograph, the NIR-SPEC instrument, and the NIRISS instrument. The results have been intriguing, but difficult to interpret definitively. Some observations revealed hints of absorption features that could be consistent with methane in the planet's atmosphere. Methane would be exciting because it is a gas that, on Earth, is produced both by geological processes and by life. Finding methane on an exoplanet is not proof of life, far from it, but it would be a significant discovery and a potential biosignature worth investigating further. However, the interpretation of these methane signals has proven to be extremely challenging. The problem lies with the star itself. TRAPPIST-1 is an M8 dwarf, one of the coolest types of stars known. It is only slightly larger than the planet Jupiter, with a radius about 1.12 times Jupiter's radius. Its atmosphere is complex and not well understood. The star has its own spectral features, absorption lines from molecules in its atmosphere, and these can interfere with or mimic the signals we might expect from a planet's atmosphere. When we observe a transit and measure the spectrum of light passing through the planet's atmosphere, we are actually measuring the combined spectrum of starlight, plus any modifications caused by the planet's atmosphere. But if the star's spectrum has features in the same wavelengths where we expect planetary signals, it becomes very difficult to separate the two. A research team led by Sukrit Ranjan at the University of Arizona conducted detailed modeling of TRAPPIST-1e's potential atmosphere, simulating different scenarios where the planet might have a methane-rich atmosphere, similar to Saturn's moon Titan. They evaluated the probability of each scenario given the observed data. Their conclusion was cautious. While the tentative hints of methane in the observations are interesting, they are more likely to be noise from the star's atmosphere rather than a genuine detection of methane on the planet. However, and this is important, their conclusion does not mean that TRAPPIST-1e lacks an atmosphere. It means the current data is not sufficient to confirm the presence of an atmosphere or determine its composition. The signals are ambiguous. More observations are needed. Other teams have approached the question from different angles, One study, published in 2025, used the James Webb observations to rule out certain atmospheric scenarios. They concluded that TRAPPIST-1e is unlikely to have a thick, hydrogen-rich atmosphere, like a mini Neptune. This is actually good news, because it confirms that the planet is rocky rather than gaseous. They also ruled out Venus-like and Mars-like atmospheres based on the lack of expected spectral features. But they could not definitively confirm or rule out an Earth-like nitrogen-oxygen atmosphere or other possible compositions. The current scientific consensus, as of late 2025, is that we still do not know with certainty whether TRAPPIST-1e has an atmosphere. If it does have one, it is probably not a thick hydrogen atmosphere, and it does not appear to be a Venus-like or Mars-like atmosphere based on current data. It could be a nitrogen-rich atmosphere like Earth's, possibly with traces of other gases including water vapor, carbon dioxide, and maybe methane. Or it might have no atmosphere at all, though this seems less likely given the planet's size and distance from the star. Scientists are planning more observations to try to resolve this question. One promising approach is called dual transit spectroscopy. This technique involves observing TRAPPIST-1e during a transit at the same time that TRAPPIST-1b, the innermost planet, which definitely has no atmosphere, also transits the star. By simultaneously observing two planets crossing in front of the star, with one known to have no atmosphere and one possibly having an atmosphere, astronomers can better separate stellar effects from planetary atmospheric effects. The stellar spectral features should appear in both observations equally, while any atmospheric features from TRAPPIST-1e should appear only in that planet's transit. This technique requires careful timing because the planets must transit simultaneously, which happens only occasionally due to the geometry of the system. But when it does happen, it provides a powerful way to improve the quality of the atmospheric measurements. Now, let me describe what it might be like on TRAPPIST-1e if we could somehow visit, assuming it has a substantial atmosphere and conditions amenable to human exploration with appropriate protective equipment. Approaching the planet from space, you would see a world that might look surprisingly familiar or completely alien, depending on its actual properties. If it has oceans and continents, like Earth, you might see blue oceans, brown or green land masses, and white clouds. If it is more of a uniform water world or ice world, it might appear primarily blue or white. If it has a thick, hazy atmosphere, you might not be able to see the surface at all. The TRAPPIST-1 system would present a spectacular sight from the surface of any of its planets, and TRAPPIST-1e would be no exception. The star itself would appear about 4 times larger in angular diameter than the Sun appears from Earth. Its disk would cover about 4 times the area of sky, but it would not be a bright yellow-white disk like our Sun. It would glow a deep, dark red, almost like a hot coal. The light would be dim, perhaps comparable to the light level about an hour before sunset on Earth. That deep twilight, when you can still see clearly, but the sun is no longer bright. Everything on the surface would be bathed in this eerie red illumination. Colors would appear quite different than under sunlight. Objects that appear red on Earth would look bright and vivid. Objects that appear blue or green might look dark and dim because there is little blue or green light in the star's spectrum to reflect. But the truly spectacular sight would be the other planets in the system. From TRAPPIST-1e, you would be able to see the other planets with the naked eye, and some of them would appear much larger than Venus or Jupiter ever appear from Earth. TRAPPIST-1F, the next planet outward, would appear as a disk rather than a point of light, visible as a small world hanging in the sky. During certain parts of TRAPPIST-1 Eowl's orbit, TRAPPIST-1F might appear nearly as large as our moon appears from Earth. The inner planets, B, C, and D, would also be visible, moving against the background stars. You could watch them over the course of days, observing their motion, even seeing them transit across the face of the star, if you were on the day side when this happened. A transit of TRAPPIST-1D across the star would cause a noticeable dimming, like a small eclipse. On the day side, standing on whatever surface exists there, you would see the star hanging motionless in the sky. It would never rise or set, just remain in the same position, its altitude depending on your latitude. At the substellar point, the point on the surface directly beneath the star would be directly overhead. As you move away from the substellar point, the star would appear lower in the sky, approaching the horizon as you travel toward the terminator. The landscape might be varied. If TRAPPIST-1E has oceans, they might cover portions of the day side where temperatures are warmest. The constant heating might create a hydrological cycle, with water evaporating from these oceans, forming clouds, and then precipitating as rain in regions where the air cools. You might see weather patterns dominated by the day-night circulation, with clouds forming in bands or other structures, quite different from Earth's weather. If there are continents or land masses, they might show signs of geological activity. So thus the planet is likely massive enough to maintain internal heat and possibly plate tectonics. Volcanoes might erupt, releasing gases into the atmosphere. Mountain ranges might exist where tectonic plates collide. Rivers might flow, carrying water from higher elevations down to the seas. Plant life, if it exists, and if photosynthesis has evolved, would need to adapt to the red light of the star. Chlorophyll, the green pigment that Earth's plants use to capture sunlight, is optimized for the wavelengths our sun produces, primarily in the visible spectrum with a peak in the yellow-green. But TRAPPIST-1's light peaks in the infrared and red portions of the spectrum. Plants on TRAPPIST-1e would need different pigments to efficiently capture this light. Scientists have speculated that photosynthetic organisms on planets around red dwarfs might be black or very dark in color, absorbing as much of the limited light as possible rather than reflecting green light like Earth's plants. Imagine a landscape where the vegetation is black or deep purple or dark red, a stark contrast to the green forests and grasslands we know. Animal life, if it exists, would face the challenge of seeing in the dim red light. Eyes might evolve to be very large to capture as much light as possible, or vision might rely more on infrared wavelengths rather than visible light. Other senses might be more important than vision. Echolocation like bats use, chemical sensing like snakes use, electrical sensing like sharks use. Any of these might be more useful than vision in the dim twilight conditions. Traveling to the night side would be a journey into permanent darkness. The star would drop below the horizon and never be seen again until you returned to the day side. The sky would be filled with stars, spectacularly bright without any light pollution from the absent sun. The other planets in the TRAPPIST-1 system would be visible, moving against the starry background. Depending on your location and the orbital geometry, you might see Earth from TRAPPIST-1e, a faint blue dot 40 light-years away, though you would need a telescope, as it would be too faint to see with the naked eye. The night-side landscape would be dark and cold, though not as cold as a completely airless world. The atmosphere, if present, would transport some heat from the day side, keeping temperatures moderated. You might find regions of ice, glaciers, and snow. But near the terminator, in the transition zone between day and night, temperatures might be mild enough for liquid water in the form of rivers or lakes fed by melting ice. Life on the night side, if it exists, would be very different from dayside life. Without sunlight, photosynthesis is impossible. All life would need to rely on chemical energy, either from geothermal sources like hot springs and volcanic vents, or from organic matter transported from the dayside by atmospheric circulation or ocean currents. Deep sea ecosystems on Earth provide a model. Around hydrothermal vents in the deep ocean, far from sunlight, entire ecosystems thrive, based on chemosynthetic bacteria that produce organic molecules from hydrogen sulfide and other chemicals dissolved in the vent water. Similarly, TRAPPIST-1e's night side might host ecosystems based on chemosynthesis, organisms that have never seen sunlight, living in eternal night. These organisms might be quite alien, adapted to extract energy from chemical reactions rather than photosynthesis, living in environments that would seem impossibly hostile to most Earth life. The long-term prospects for habitability on TRAPPIST-1e are generally favorable. The planet sits firmly in the habitable zone and appears to have retained its original position since formation, unlike some planets that may have migrated significantly. The star, being a red dwarf, will remain stable for trillions of years, providing a constant energy source for any life that develops. However, there are challenges. Red dwarf stars, especially young ones, are magnetically active and produce powerful flares. TRAPPIST-1 has been observed to flare occasionally, though not as frequently or as violently as some other red dwarfs. These flares could damage any life on the day side, particularly single-celled organisms or simple multicellular life without protective mechanisms. But life beneath water or beneath the surface would be shielded from most radiation. Another challenge is that we do not know the planet's history. Did it form with water, or is it a dry world? Has it always had an atmosphere? Or did it lose one early on and then develop a secondary atmosphere from volcanic outgassing? The answers to these questions would dramatically affect its habitability. In November 2018, a study by researchers at several universities concluded that of all 7 NORAPPIST-1 planets, TRAPPIST-1e has the best chance of being an Earth-like ocean planet and is the most worthy of further study regarding habitability. This assessment was based on detailed modeling of each planet's likely composition, internal structure, and position in the habitable zone. The Habitable Exoplanets Catalogue, maintained by the University of Puerto Rico at Arecibo, consistently ranks TRAPPIST-1e among the top potentially habitable exoplanets discovered. Its Earth Similarity Index, a metric that compares a planet to Earth based on size, density, escape velocity, and surface temperature, is among the highest for any confirmed exoplanet. But rankings and indices, while useful, do not tell us whether the planet is actually inhabited. That requires direct observation, searching for biosignatures. Over the coming years, James Webb will continue to observe TRAPPIST-1e, accumulating more data, improving signal-to-noise ratios, and hopefully providing clearer answers about its Atmospheric composition. If we do eventually confirm an atmosphere and detect water vapor, carbon dioxide, oxygen, or other gases that suggest habitability or even life, TRAPPIST-1 would become one of the most important worlds in exoplanet science. It would be a primary target for all future telescopes and missions. Plans for even more powerful observatories would likely include TRAPPIST-1e as a key science target. For now, we can only observe and theorize. TRAPPIST-1e remains enigmatic, a world that might be the closest truly Earth-like planet we have found, or might be a barren rock despite its promising properties. Time and more observations will tell. But one thing is certain, this planet, orbiting an unassuming red dwarf 40 light-years away, has captured our imagination and will remain a focus of intense scientific scrutiny for decades to come. Planet 4, Kepler 442b. Not all potentially habitable exoplanets orbit red dwarf stars. Some orbit stars more similar to our Sun, and these systems present their own unique advantages and challenges for habitability. One of the most promising Earth-like planets we have discovered orbits a K-type star, an orange dwarf that is smaller and cooler than our Sun, but larger and hotter than the red dwarfs that host most of the other planets we have discussed. This planet represents a different approach to habitability, a world that might avoid some of the challenges faced by planets around red dwarfs, while still sitting firmly in the habitable zone. It is called Kepler 442b, and for several years after its discovery, it was considered by many astronomers to be one of the single most promising candidates for a habitable world ever found. Kepler 442b is located approximately 1,196 light-years away from Earth, about 1,200 light-years depending on which recent distance measurement you use. In the constellation Lyra, this is much farther than the other planets we have discussed, which creates significant challenges for detailed study. But the planet's properties are so intriguing that it remains a high-priority target for exoplanet research, despite the distance. The planet was discovered by NASA's Kepler Space Telescope, one of the most successful planet-hunting missions in history. Launched in March 2009, Kepler stared at a single patch of sky containing about 150,000 stars, measuring their brightness continuously for over 4 years, searching for the tiny dips in brightness that indicate a planet transiting across the star's face. Kepler discovered over 2,600 confirmed exoplanets and identified thousands more candidates awaiting confirmation before a mechanical failure in 2013 ended its prime mission. Kepler 442b was announced on January 6, 2015, as part of a batch of new planet discoveries that included several other notable potentially habitable worlds. The whole announcement was based on observations collected between May 2009 and March 2012, over 3 years of continuous monitoring that revealed multiple transits of the planet. Let me describe this world's properties in detail. Kepler 442b is a super-Earth, an exoplanet with a radius larger than Earth's but smaller than Neptune's. Its radius is about 1.34 times Earth's radius, making it noticeably larger than our world, but not so large that it must be a gas giant. With a radius of 1.34 Earth radii, Kepler 442b sits right on the uncertain boundary between rocky super-Earths and mini-Neptunes. Here is the challenge. We do not have a direct mass measurement for Kepler 442b. The Kepler telescope could detect transits and measure planet sizes, but it could not measure planet masses. Mass measurements require the radial velocity technique, which involves measuring the tiny wobble the planet induces in its star's motion. For planets as far away as Kepler 442b, this is extraordinarily difficult with current instruments because the star is quite faint, making precise spectroscopy challenging. Without a direct mass measurement, we must estimate the mass from the radius using mass-radius relationships derived from planets we have measured more completely and from theoretical models. These estimates suggest Kepler 442b has a mass of about 2.36 Earth masses, though this carries significant uncertainty. Some models suggest it could be anywhere from 1.5 to 3 Earth masses, depending on its composition. If the planet is rocky with an Earth-like composition, its mass would be on the lower end of that range. If it has substantial water or ice, contributing mass, but not as much density, the mass might be higher. If it has a thick hydrogen atmosphere that contributes to its radius without much mass, the mass might be lower. The truth is, we simply do not know for certain. However, based on the most recent statistical analyses of planets in this size range, a radius of 1.34 Earth radii suggests the planet is probably rocky. According to research by Ethan Siegel and others, planets with radii up to about 1.5 or 1.6 Earth radii are likely to be rocky super-Earths rather than mini-Neptunes, though there is a transition zone around 1.6 to 1.7 Earth radii, where it becomes much less certain. Kepler 442b at 1.34 Earth radii is probably rocky, making it a legitimate candidate for habitability. The planet orbits a K-type star designated Kepler 442. K-type stars, also called orange dwarfs, are intermediate between red dwarfs, M-type stars, and yellow dwarfs like our Sun, G-type stars. Kepler 442 has about 61% of the Sun's mass and about 60% of the Sun's radius. Its surface temperature is approximately 4,402 Kelvin compared to the Sun's 5,778 Kelvin, giving it an orange color rather than the Sun's yellow-white or the deep red of M dwarfs. The star's age is estimated at about 2.9 billion years, with substantial uncertainty in that estimate. It is younger than our Sun, which is about 4.6 billion years old, but old enough that any life on orbiting planets would have had billions of years to develop. Kepler 442b orbits this star every 112.305 days, a little under 4 Earth months. The semi-major axis of the orbit, the average distance from the star, is about 0.409 astronomical units, roughly 40% of the distance between Earth and the Sun. This places the planet well within the habitable zone of its star. Now, here is what makes this orbital distance particularly interesting. At 0.41 astronomical units from a K-type star, tidal forces are not strong enough to have definitely locked the planet's rotation to its orbit. The planet might still be rotating, experiencing day and night cycles like Earth does. Tidal locking depends on several factors, the planet's distance from the star's mass, the planet's mass and size, and how much time has elapsed. Closer planets lock faster. More massive stars exert stronger tidal forces. Smaller, less massive planets lock faster than larger, more massive ones. And of course, the longer time passes, the more likely locking becomes. For Kepler 442b at 0.41 AU from a 0.61 solar mass star, calculations suggest that tidal locking may not have occurred yet after 2.9 billion years. The planet might have a rotation period of something like 20 to 40 hours, creating a day-night cycle. This would be enormously beneficial for habitability. A day-night cycle moderates temperatures across the planet. The day side does not get as hot as it would if the sun never set. The night side does not get as cold as it would if the sun never rose. The entire planet benefits from a more even distribution of temperatures, making a larger fraction of the surface potentially habitable. It also benefits any life that might evolve. On Earth, the day-night cycle influences the behavior and evolution of nearly all organisms. Plants open and close their leaves or flowers based on the cycle. Animals have circadian rhythms tuned to the 24-hour day. The day-night cycle may be important for regulating biological processes and might make the development of complex life easier. As of July 2018, Kepler 442b was considered the most habitable, non-tidally locked exoplanet discovered. This is a significant distinction because it suggests the planet might avoid some of the challenges that tidally locked planets face. The amount of stellar energy Kepler 442b receives is about 70% of what Earth receives from the Sun. This is less than Earth, but considerably more than Mars, which receives only about 43%. With an Earth-like atmosphere and greenhouse warming, 70% of Earth's solar constant should be more than sufficient to maintain liquid water over much of the planet's surface. The planet's equilibrium temperature, assuming no atmosphere, is estimated at about 233 Kelvin, which is minus 40 degrees Celsius or minus 40 degrees Fahrenheit. But again, this is without greenhouse warming. Add an atmosphere with carbon dioxide, water vapor, and other greenhouse gases, and the surface temperature could be well above freezing, perhaps ranging from minus 10 to plus 20 Celsius, depending on the exact atmospheric composition and pressure. If Kepler 442b is indeed rocky and has an Earth-like composition, surface gravity would be about 30% stronger than Earth's. This is noticeable, but not crushing. A person who weighs 150 pounds on Earth would weigh about 195 pounds on Kepler 442b. Athletic activities would be more challenging. Climbing stairs would be more tiring. But it would not be like the 3 times Earth gravity of LHS 1140b. Humans could probably adapt to it, and any native life would obviously be adapted from the start. K-type stars like Kepler 442 have several advantages as hosts for habitable planets. They are more stable than M-type red dwarfs, producing fewer and less intense flares. This reduces the risk of atmospheric stripping and radiation damage to any life on the planet. They are longer lived than G-type stars like our Sun, with lifespans ranging from 18 to 34 billion years, giving life much more time to evolve than the 10 billion years our Sun will last. And their habitable zones are at distances where tidal locking is not guaranteed, allowing planets to maintain rotation and day-night cycles. These factors led some astronomers to suggest that K-type stars might be the best stellar type for hosting habitable planets, better than either red dwarfs or Sun-like stars. They provide stability, longevity, and moderate conditions without the extreme challenges of red dwarfs or the shorter lifespans of Sun-like stars. However, K-type stars also have a challenge. They are less common than M-type red dwarfs, which make up about 70% of all stars in the galaxy. K-type stars constitute about 12% of all stars. This means there are fewer of them to search, reducing the total number of potentially habitable planets around such stars. Now let me describe what Kepler's might be like if we could somehow visit. The biggest obstacle, of course, is the distance. At 1200 light-years, Kepler 442b is about 280 times farther from us than Proxima Centauri b and about 25 times farther than TRAPPIST-1 Eon. With any propulsion system we can currently envision, the journey would take tens of thousands or hundreds of thousands of years. But imagine, for the sake of exploration, that we could instantly transport ourselves there. Approaching from space, you would see a world that might look remarkably Earth-like if conditions are right. With a day-night cycle and an atmosphere, the planet could have dynamic weather patterns, clouds swirling in the atmosphere, possibly visible bands or storms if the atmospheric dynamics create such features. If the planet has oceans and continents, you would see a mix of blue water and land masses. The color of the land would depend on what is there. If vegetation has evolved, it might appear green like Earth's plants, or it might be a different color depending on what pigments the local photosynthetic organisms use. The star Kepler 442, being orange rather than yellow, produces a slightly different spectrum than our Sun, which might influence what colors are most efficient for photosynthesis. Landing on the surface, assuming there is solid ground and not just a global ocean, you would find gravity about 30% stronger than Earth's. Every movement would require more effort. Your body would feel heavier. But assuming you are reasonably fit and have had some time to acclimate, you could function, though you would tire more quickly than on Earth. The star Kepler 442 would appear about 50% larger in angular diameter than the Sun appears from Earth, subtending roughly 0.75 degrees across, compared to the Sun's 0.5 degrees. It would glow with an orange light rather than yellow-white. The illumination would feel somewhat dimmer than sunlight on Earth, perhaps comparable to a slightly overcast day, but still bright enough for all normal activities. The day-night cycle, if the planet is indeed rotating and not tidally locked, might be anywhere from 20 to 50 hours, depending on the actual rotation rate. A longer day than Earth's 24 hours would mean longer daylight periods and longer nights. Organisms would need to adapt to this different rhythm, but it is certainly not incompatible with life. If the planet has an Earth-like atmospheric pressure and composition, you could potentially breathe the air, though you would want to verify the oxygen content first. Earth's atmosphere is about 21% oxygen, which is unusually high in cosmic terms. Oxygen is a reactive gas that does not persist without constant replenishment. On Earth, photosynthetic life produces oxygen or as a waste product, maintaining the high atmospheric concentration. If Kepler 442b has photosynthetic life, its atmosphere might have oxygen too, though possibly at a different concentration. The landscape could be varied. If the planet has plate tectonics like Earth, you might find mountain ranges where tectonic plates collide, rift valleys where they pull apart, volcanoes where magma rises from the mantle. Rivers would flow from high elevations to low, carving valleys and canyons over millions of years. Erosion would shape the surface, creating diverse terrain. If there are oceans, they might be similar to Earth's or quite different depending on factors like salinity, temperature, and depth. The presence of a day-night cycle would create tides if the planet has a moon. Or even without a moon, the star's gravity could create small solar tides. Ocean currents would develop, driven by temperature differences, winds, and the planet's rotation. Weather would be influenced by the rotation rate, atmospheric composition, and the distribution of land and water. If the day is longer than Earth's 24 hours, the day side would have more time to heat up, and the night side more time to cool down, potentially creating larger temperature swings. But the atmosphere would moderate these swings, and the overall climate might be quite temperate, especially in a band around the equator. Life, if it exists, would have had billions of years to evolve, with at least 2.9 billion years since the star formed, and likely the planet formed shortly after. That is more than half the age of life on Earth. On Earth, life appeared within the first billion years and remained single-celled for most of its history. Multicellular life did not arise until about 600 million years ago. But once multicellular life appeared, evolution proceeded relatively quickly, producing the incredible diversity we see today. On Kepler 440b, if life followed a similar trajectory, there might be complex ecosystems, diverse organisms filling various ecological niches, photosynthetic organisms forming the base of the food chain, herbivores feeding on them, predators hunting the herbivores, decomposers breaking down dead organic matter and recycling nutrients. The higher gravity might influence evolution. Organisms might be more robust, with stronger skeletal structures to support their weight. Flight would be more difficult, requiring more power to overcome the stronger gravity. So flying creatures might be smaller or rarer than on our Earth. Aquatic life would be less affected by gravity due to buoyancy, so oceans might be particularly rich in life. Intelligence might have evolved. The planet has been around long enough. If environmental conditions favored the evolution of intelligent tool-using species, civilization might exist. However, the higher gravity could make space travel more challenging for any native species. Rockets require more fuel to achieve orbit from a higher gravity world, making the technological hurdle to space exploration higher. The prospects for habitability on Kepler 442b are excellent based on what we know. The planet is the right size, orbits in the habitable zone of a stable star, receives a reasonable amount of stellar energy, and probably rotates rather than being tidally locked. If it has water and an atmosphere, it could be remarkably Earth-like. But the enormous distance creates a fundamental problem. We cannot study this planet in detail with current technology. The star is too faint and too far away for precise radial velocity measurements that would give us the planet's mass. The distance is too great for James Webb to study the atmosphere with transmission spectroscopy, even if we had thousands of hours of observing time to dedicate to it. Future telescopes might change this. The concept for a habitable worlds observatory, a space telescope specifically designed to study potentially habitable exoplanets, includes capabilities that might allow atmospheric studies of planets around bright nearby stars. But Kepler 442b is too far, and its star is too faint for even these next-generation instruments to study effectively. We might need to wait decades or even centuries for technology that can definitively tell us whether Kepler 442b has an atmosphere, whether it has water, whether it might host life. In the meantime, it exists as a tantalizing possibility, a world that on paper looks nearly perfect for life, but which we cannot yet confirm is actually habitable. Kepler 442b reminds us that the galaxy is full of potentially habitable worlds. The Kepler mission alone found dozens of planets in the habitable zones of their stars. Many of these are too far away to study in detail, but they are there, real places, existing right now. some of them perhaps teeming with life, others perhaps barren rocks. We do not know which is which, and with current technology, we cannot find out for the most distant ones. But knowing they exist matters. It tells us that habitable planets are common, not rare. It tells us that in a galaxy with hundreds of billions of stars, there might be billions of potentially habitable planets. And if even a tiny fraction of those actually host life, the galaxy could be filled with living worlds. Kepler 442b, one of the most Earth-like planets ever found, sits 1,200 light-years away, forever beyond our direct reach, but never beyond our imagination. A world that might be home to ecosystems as complex as Earth's, perhaps even to intelligence and civilization. Or might be empty, an ocean world or ice world without life. We cannot say which, but it is there, orbiting its orange sun, whether anyone is watching or not. Planet 5, Gliese 12. In May 2024, astronomers announced a discovery that immediately rocketed to the top of the most wanted list for atmospheric studies. A planet located just 40 light-years away, roughly the same size as Earth, with an estimated surface temperature warm but not too hot, orbiting within the habitable zone of its star. A planet close enough to study in detail with existing and near-future telescopes. A planet that might help us understand one of the greatest mysteries in planetary science: why Venus became a hellish greenhouse, while Earth remained habitable despite both planets starting from similar conditions. They called it Gliese 12b, and within hours of the announcement, it was being hailed as one of the most important exoplanet discoveries in years. Gliese 12b orbits a red dwarf star called Gliese 12, located in the constellation Pisces. The star is small even by red dwarf standards, with only about 27% of the Sun's radius and about 7% of the Sun's luminosity. It is an M3.5V star, which means it is slightly warmer and more luminous than the dimmest M dwarfs, like TRAPPIST-1, but still cool and faint compared to the Sun. The planet was discovered using the Transiting Exoplanet Survey Satellite, or TESS, NASA's planet-hunting space telescope that launched in 2018. TESS surveys the entire sky over 2 years, dividing it into sectors and observing each sector for about a month, searching for transits. When TESS detected periodic dips in Gliese 12's brightness, ground-based telescopes quickly followed up to confirm the planet and measure its properties. The discovery was actually announced in 2 separate papers, published simultaneously, one led by Masayuki Kuzuhara of the Astrobiology Center in Tokyo, Japan, and another led by Shishir Dholakia of the University of Southern Queensland in Australia. Both teams independently analysed the test data and conducted follow-up observations, and both reached similar conclusions about the planet's properties. This independent confirmation added confidence to the discovery. Let me describe Gliese 12b in detail. The planet's radius is about 0.96 Earth radii, or roughly 96.6% of Earth's size. This makes it slightly smaller than Earth, but larger than Venus, which has a radius of 0.95 Earth radii. In terms of size, Gliese 12b is nearly a twin of Earth or Venus. Recent mass measurements published in late 2025, using data from multiple high-precision spectrographs, including HARPS-N, ESPRESSO, and CARMENES, determined that the planet's mass is about 3.75 Earth masses, with an uncertainty of about plus or minus 0.4 Earth masses. This is significantly more massive than Earth, despite being similar in the size. The combination of a slightly smaller radius but much higher mass means Gliese 12b is substantially denser than Earth. Its density is estimated at about 9.3 grams per cubic centimetre compared to Earth's 5.5. This high density strongly suggests that Gliese 12b has a large iron core relative to its total size, or is composed of materials even denser than Earth's iron silicate composition, though the latter seems less likely. A large iron core would mean the planet's interior is dominated by metal rather than rock. This might seem strange, but simulations of planet formation show that under certain conditions, planets can form with very different rock-to-metal ratios than Earth. If Gliese 12b formed closer to its star, where temperatures were higher, the ice and volatile materials that contribute to Earth's mass might have been absent, leaving a higher proportion of iron and other heavy elements. The high density and mass have important implications for the planet's surface gravity. Despite being slightly smaller than Earth, Gliese 12b's surface gravity is about 2.2 times Earth's gravity. This is substantial, but not quite as extreme as LHS 1140b's 3 times Earth gravity. Still, a person who weighs 150 pounds on Earth would weigh about 330 pounds on Gliese 12b, making movement significantly more challenging. The planet orbits its star every 12.8114 days at a distance of 0.0662 astronomical units, about 6.6% of the distance between Earth and the Sun. At this distance from such a cool, dim star, the planet receives about 1.6 times the stellar energy that Earth receives from the Sun. This is more energy than Earth, but significantly less than Venus, which receives about 1.9 times Earth's solar constant. This energy level places Gliese 12b right at a critical boundary. It is warm enough that it could potentially have a runaway greenhouse effect like Venus, but it is also cool enough that with the right atmospheric conditions, it could maintain liquid water. Understanding which path the planet has taken is one of the key questions scientists want to answer. The planet's equilibrium temperature, the temperature it would have with no atmosphere, is estimated at about 315 Kelvin, or 42 degrees Celsius, 107 degrees Fahrenheit. This assumes the planet reflects about the same fraction of light as Earth does. If the planet is darker and absorbs more light, it would be warmer. If it is brighter and reflects more light, it would be cooler. 42 degrees Celsius is warm, comparable to a hot summer day in a desert, but not unbearably so. It is well below the boiling point of water. If Gliese 12b has only a thin atmosphere, or no atmosphere at all, surface temperatures might be in this range, warm but potentially tolerable for certain types of life, especially if water exists in cooler regions like poles or at higher elevations or deep underground. But if the planet has a thick atmosphere with greenhouse gases, temperatures could be much higher. Venus, with its thick carbon dioxide atmosphere, creating an intense greenhouse effect, has a surface temperature of about 735 Kelvin, or 462 degrees Celsius, hot enough to melt lead. A runaway greenhouse on Gliese 12b could create similarly extreme conditions. So which is it? Does Gliese 12b have a thin atmosphere and moderate temperatures, making it potentially habitable? Or does it have a thick greenhouse atmosphere, making it a hellish Venus analogue? This is the critical question. Early observations from James Webb in 2025 provided some clues, but not yet a definitive answer. The observations confirm that Gliese 12b Almost certainly it does not have a thick hydrogen-helium atmosphere like a mini Neptune. This is good news because it confirms the planet is rocky rather than gaseous. The observations also found no clear evidence of a thick carbon dioxide atmosphere like Venus has. This is intriguing. If Gliese 12b were a Venus analog, we would expect to detect strong carbon dioxide absorption features, and we do not see them. This suggests the atmosphere is either thin, or if it is thick, it must be composed of something other than carbon dioxide. One possibility is a nitrogen-dominated atmosphere like Earth's. Nitrogen is difficult to detect through transmission spectroscopy because it does not absorb infrared light strongly in the wavelengths James Webb observes. An Earth-like atmosphere would be nearly invisible to JWST's instruments, appearing as almost no atmosphere at all. Another possibility is that the planet truly has little or no atmosphere. It might be like Mercury or the Moon, with only a very thin exosphere of particles, occasionally knocked off the surface by micrometeorite impacts or solar wind interactions. Scientists are conducting additional observations and refining their analysis techniques to try to distinguish between these possibilities. The planet is close enough and transits a small enough star that detailed atmospheric studies are feasible with current technology, making it a high-priority target. What makes Gliese 12b scientifically important, beyond just being another potentially habitable planet, is its position between Earth and Venus in terms of stellar energy received. Venus is often called Earth's twin because the two planets are similar in size. But Venus is a cautionary tale about habitability. Despite being in the habitable zone, according to some definitions, Venus is utterly inhospitable, with crushing atmospheric pressure, temperatures hot enough to melt lead, and clouds of sulfuric acid. Scientists believe Venus was not always like this. Early in solar system history, Venus might have had liquid water oceans and a temperate climate. But over hundreds of millions or billions of years, a runaway greenhouse effect transformed it into the hellscape we see today. Understanding why this happened is crucial for understanding habitability. The runaway greenhouse process works like this. As a planet receives more solar energy, or as greenhouse gases accumulate in the atmosphere, surface temperatures rise. Warmer temperatures cause more water to evaporate from oceans. Water vapor is itself a greenhouse gas, which traps more heat, causing temperatures to rise further, which causes more evaporation. This positive feedback loop can spiral out of control. Eventually, so much water vapor accumulates in the atmosphere that ultraviolet light from the sun can break apart the water molecules. Hydrogen escapes to space, and the oxygen either escapes or reacts with surface materials. Over time, all the water is lost, leaving a thick carbon dioxide atmosphere and scorching temperatures. Says this is what happened to Venus. But why did not it happen to Earth? Earth receives less stellar energy than Venus, which is part of the answer. But there are other factors. Earth has plate tectonics that help regulate carbon dioxide through the carbon-silicate cycle. Earth has a strong magnetic field that helps protect the atmosphere. Earth might have had fortunate timing in when water was delivered and how quickly it cooled after formation. Gliese 12b receives more energy than Earth, but less than Venus. If it has lost its atmosphere, it suggests that planets around red dwarfs have difficulty retaining atmospheres, even when they are in the habitable zone, which would be discouraging for the prospects of life around such stars. But if it has retained an atmosphere, and especially if that atmosphere is temperate, rather than undergoing a runaway greenhouse. It would suggest that habitable planets around red dwarfs are possible, despite the challenges. The planet's proximity at 40 light-years makes it an ideal target for study. Ground-based telescopes can measure its mass precisely with radial velocity. James Webb can study its atmosphere with transmission spectroscopy during transit. Future missions might even attempt direct imaging, though this remains extraordinarily challenging, even for nearby planets. Now, what would it be like to visit Gliese 12b, assuming we could overcome the distance? The experience would depend entirely on whether the planet has an atmosphere and what that atmosphere is like. If the planet is airless or nearly airless like Mercury, landing would place you on a hot, barren surface baked by the red star overhead. Surface temperatures during the day might reach 40 to 50 degrees Celsius or higher. The star would appear much larger than the Sun, about 3 times the angular diameter, glowing dull red. There would be no wind, no weather, no sound except what you create yourself, since sound requires a medium like air to propagate. The surface might be rocky, cratered by impacts, with no erosion to smooth features, since erosion requires an atmosphere. You would need a spacesuit not for pressure, but for temperature control and to provide breathable air. The high gravity would make every movement more tiring, and you would need to be careful not to injure yourself with the increased weight. If the planet has a thin atmosphere, perhaps a few percent of Earth's atmospheric pressure, the experience would be somewhat different. There might be some wind, some weather, though much less dramatic than Earth's. The atmosphere might be visible as a haze on the horizon. The sky might have colour, though likely quite different from Earth's blue. Landing would be easier with an atmosphere to provide some aerobraking, but you would still need a full pressure suit to survive. If the planet has an Earth-like atmosphere, things become interesting. The air might be breathable, though. You would want to verify the oxygen content and check for any toxic gases first. The surface temperature of 40 degrees Celsius would feel hot but tolerable, similar to a hot day in many Earth locations. Higher elevations or polar regions might be cooler and more comfortable. You would experience much higher gravity than Earth, making physical activity strenuous. Climbing stairs or hills would be exhausting, but assuming you are reasonably fit and can acclimate, you could function, though you would need to be careful not to overexert yourself. The star would dominate the sky, appearing much larger than the Sun and glowing red. The landscape would be bathed in red light, making colors appear different than under sunlight. The planet is likely tidally locked, so the star would hang in the same position in the sky, never rising or setting. This would create a permanent day side and night side, with all the implications we have discussed for previous planets. If the planet has a thick, Venus-like atmosphere, landing would be impossible with current technology. The atmospheric pressure would be crushing, and temperatures would be hot enough to melt many metals. You would be in a spacecraft that could withstand these conditions, or high in the atmosphere, in the cooler, lower pressure regions, but surface access would be completely impossible. The prospects for life on Gliese 12b depend almost entirely on atmospheric conditions we have not yet determined. If the planet has a temperate atmosphere with liquid water, life could potentially exist, especially in cooler regions. If it is airless or has a thin atmosphere, life seems unlikely, though not impossible, if subsurface water and geothermal heat provide habitable niches. if it has undergone a runaway greenhouse, life as we know it is impossible. The next few years of observations will be crucial. Multiple research teams are working on more James Webb observations. Ground-based telescopes continue to refine the mass, measurement and search for any variations that might indicate additional planets in the system or unusual orbital dynamics. Gliese 12b represents something important in exoplanet science, a nearby laboratory for understanding the boundary between habitable and uninhabitable. By studying this planet, we learn not just about Gliese 12b itself, but about the conditions that allow planets to remain habitable. This knowledge will help us assess the habitability of many other exoplanets and understand the factors that make Earth habitable. The planet also reminds us that being in the habitable zone is necessary but not sufficient for habitability. Atmospheric properties matter enormously. A planet at the right distance from its star can still be inhospitable if it loses its atmosphere or develops a runaway greenhouse. Understanding these processes is essential for the search for life. Over the coming years, Gliese 12b will be one of the most studied exoplanets. It is close enough, transits a small enough star, and has uncertain enough atmospheric properties that detailed study is both possible and scientifically valuable. Each observation brings us closer to understanding whether this world is habitable, whether it might host life, or whether it is another Venus, a cautionary example of a world that went wrong. For now, it remains one of the 5 most promising potentially habitable planets we know. A world that might be temperate and Earth-like, or might be hot and hostile. But either way teaches us something crucial about planetary habitability. What these discoveries mean. We have now explored 5 worlds in detail. Proxima Centauri b, the planet next door, orbiting the nearest star, possibly tidally locked, but in the habitable zone. LHS 1140b, the possible ocean world, with hints of a nitrogen atmosphere and vast amounts of water. TRAPPIST-1e, perhaps the most Earth-like world in a remarkable 7-planet system, with observations suggesting possible atmospheric retention despite orbiting a red dwarf. Kepler-442b, the super-Earth around a stable orange dwarf, possibly rotating and experiencing day-night cycles, tantalizingly Earth-like, but too far away for detailed study. And Gliese 12b, the recently discovered exovenus that might help us understand the boundary between habitable and runaway greenhouse conditions. Each of these worlds is unique. Each presents different opportunities and challenges for habitability. Each teaches us something about the incredible diversity of planetary systems in our galaxy. But taken together, they tell us something profound. Potentially habitable planets are not rare anomalies, but common features of the galaxy. Consider the statistics. In our immediate cosmic neighborhood, within 50 light-years of Earth, we have found at least 3 planets in habitable zones. Proxima b at 4 light-years, TRAPPIST-e at 40 light-years, LHS 1140b at 48 light-years, and Gliese 12b at 40 light-years. That is 4 potentially habitable planets within a radius that contains perhaps 1,500 to 2,000 stars. If this ratio holds across the galaxy, and there is no reason to think it should not, the Milky Way's estimated 200 to 400 billion stars could host tens of billions of potentially habitable planets, perhaps 100 billion or more. Not all of these will actually be habitable. Some will have lost their atmospheres. Some will have runaway greenhouse effects. Some will be too dry or too wet or have other properties that prevent life. But even if only 1% of potentially habitable planets are actually habitable, that still means hundreds of millions of habitable worlds in our galaxy alone. And if even a small fraction of those habitable worlds actually host life, the galaxy could contain millions or tens of millions of living worlds. Life might be common, not rare. We might live in a biological universe, not a dead one. This is speculation, of course. We do not know if any of these 5 planets actually host life. We have not detected any biosignatures, any clear evidence of living organisms. But the mere existence of so many potentially habitable worlds so close to us suggests that the question is not whether life exists elsewhere, but where and how common it is. The detection of life on another world would be the most profound scientific discovery in human history. It would tell us that we are not alone, that life is not a unique accident on Earth, but a natural outcome of the right conditions. It would raise new questions. Is this life based on the same DNA and RNA chemistry as Earth life? Did it arise independently? Or could there be a connection through panspermia, life seeding from one world to another? How common is complex life? How often does intelligence evolve? But even if we do not find life on these 5 planets, the search will continue. We have barely begun to explore the exoplanet population. New planets are discovered regularly. New techniques allow us to study them in ever greater detail. Each year brings new data, new insights, new possibilities. The 5 planets we have discussed tonight are the first generation of potentially habitable worlds that we can actually study in detail. Future generations of telescopes will find more. The Habitable Worlds Observatory, if it is built as planned, will specifically target potentially habitable planets around nearby sun-like stars, searching for biosignatures. Ground-based, extremely large telescopes will image exoplanets directly, studying their atmospheric composition and searching for signs of seasons, weather, even surface features. Within our lifetimes, or certainly within our children's lifetimes, we might have definitive answers about these worlds. We might know which ones have atmospheres, which have water, which have conditions truly suitable for life. We might even detect life itself, seeing the unmistakable chemical signatures of biological activity in the spectrum of light from a distant world. This is the frontier of science, the boundary between what we know and what we are discovering. These 5 planets, Proxima b, LHS 1140b, TRAPPIST 1e, Kepler 442b, Gliese 12b, are waypoints on a journey that has just begun. A journey to understand our place in the universe and to answer the question that has haunted humanity since we first looked up at the stars. Are we alone? Thank you for joining me on this extensive journey through some of the most fascinating worlds ever discovered. If you found this exploration valuable, please like and subscribe. Your support helps me create more of this detailed, thoughtful content. Look up tonight at the stars. Some of them have planets, and some of those planets might be home to life, existing right now, 40 or 50 or 1,000 light years away, completely unaware that we are looking for them. The universe is vast, but it is not empty. These 5 worlds prove that, and the search, the great search for life beyond Earth, continues. Good night, and may you never look at the stars the same way again.